All right, this is Mr. Baker, and we are going to be working Forrester's Algebra test number 17. Test number 17. Looking at questions 1 through 6, they deal with the squaring of a binomial in one step. And just to refresh your memory on that, we had a formula for squaring the binomial. And if the binomial is in the form first plus last squared, we said that we can use FOIL. We could just write it out 2 times and go, it's first plus last times first plus last, and then do the FOIL, which would be the first times the first, plus the outside, which would be the first times the last, plus the inside, which would be the last times the first, plus the last squared for FOIL. But in this lesson, we learned that we could also do a square of a binomial, and this only works for squares. This will work for any binomial, but in this case, for a square, the formula would be first squared plus 2 first last plus last squared. So we write our binomial, whatever the first term is, we're going to square it. Then we're going to add to that the product of 2 times the first times the last, and then the last squared. So let's go ahead and do numbers 1 through 6 using that method. That's why the question says writing only the given expression and then the answer. They're trying to get you to go through and do the math mentally without using the FOIL method. So, question number 1. They'd like us to square x plus 8 quantity squared. So using this format, we see that that's going to produce x squared, because the first term is x, the last term being 8. So first squared is x squared plus 2 times x times 8, which is the same as 2 times 8 times x. 2 times 8 is 16, times x gives us 16x. And the last term of 8 times 8, 8 squared, 8 times 8 is 64. So the answer is x squared plus 16x plus 64. Number 2. Number 2 is x minus 11 squared. Same process. First squared is going to be, first is x, and so first squared is again going to be x squared. Now, we're going to add to that 2 times the first times the last. Remember that x minus 11 squared could be written as x plus a negative 11. And so what we need to remember here is the first times the last times 2 would actually be x times negative 11 times 2. The negative 11 gives us negative 22x. Or in this case, so it's x squared plus a negative 22x, and then 11 times 11 is 121. Now, adding a negative is the same as subtracting a positive, so this is not incorrect, but it would be more accurately written x squared minus 22x plus 121. Number 3. Quantity 5x plus 3, and that quantity is squared, which is going to be the first term, 5x squared. 5x times 5x. Well, if we just had x, it would be x squared, but we don't. We have 5x. So we have to remember to square the coefficient before the x. 5 times 5 is 25. X times x is x squared. So 5x times 5x is 25 x squared plus 2 times first times last. Well, 2 times last, let's do that one first, because 2 times last would be 6 times first. 6 times 5x gives us 30x, and then the last squared plus 3 times 3 is 9. So the answer to number 3 is 25x squared plus 30x plus 9. Number 4. Number 4 is x minus 7y squared. Okay, the first in this case, if we consider it to be x, so we're going to square the x, gives us x squared. And then we have plus 2 times first times last. Now, 2 times first would be 2x times last is minus or negative 7y. 2 times first times last is going to give us negative 14xy. And then last squared, negative 7 times negative 7 is positive. Negative times negative is positive. 7 times 7 is 49. Y times y is y squared. So x squared minus 14xy plus 49 squared is the answer to number 4. Number 5. (10c) plus 7m quantity squared. Okay. The first term here is 10c. 10c squared would be 10 times 10, which is 100, times c, or c squared. So it's going to equal 100 c squared. That's the first term squared. Plus 2 times first, which would be 2 times 10c, which gives us 20c, times the last, which is 7m. 20 times 7 is 140, and c times m is cm, plus last squared. The last is 7m. 7m squared is 7 times m times 7 times m. That's the same as 7 times 7 times n, m times m. 7 times 7 is 49. And n times m is m squared. So the answer to number 5 is 100c squared plus 140 cm plus 49m squared. And lastly, number 6. Is quantity A minus B quantity squared. All right. Well, first term is A. A times A is A squared. Plus 2 times first, 2 times A, times B, which is, consider it negative B. 2 times A times B is minus 2A B. And then the last is negative B times negative B, or positive B squared. A squared minus 2AB plus B squared is the answer to number 6. Number 7 asks us to multiply the quantity x plus 5 times the quantity 2x minus 7. Now we can't use this shortcut that we've been using up to this point of first squared plus 2 first last plus last squared, because this is not the square. This is not a squaring of a binomial. This is multiplying two binomials. And so we're going to go ahead and use the FOIL method for this. So remember, the FOIL is first times first, which would be, in this case, x times 2x, or 2x squared. The outsides, which is x times negative 7, or minus 7x. The insides, which in this case is 5 and 2x, which gives me plus 10x. And lasts, which positive 5 times negative 7 is negative 35. Now, because this was a FOIL and not a perfect squaring of a binomial, I need to go back and combine my like terms, and we're going to find like terms that need to be consolidated in the center where our outside inside terms are at. So we have 2x squared, it's minus 7x plus 10x, or that net here of plus 3x minus 35. Let me check that real quick. Number 7, 2x squared plus 3x minus 35. That checks. That is the answer to number 7. Question number 8. They've asked us to factor p squared minus 49. P squared minus 49. Okay. So we're kind of working this one backwards, rather than you recognizing here that we are factoring a trinomial square. Let me go back on that just for a second. All right, let's go ahead and look at number 8 here. Number 8 is p squared minus 49. And you can see in this that you're going to end up with, maybe you can start to see the pattern here. Let's go ahead and just take a look at this. We know we're going to factor this out into being two different binomials. In order for us to have p squared, we have to have a first term, first time first, each of those being p, right? P times p is going to be p squared. If we were doing this in reverse, remember, we're going to come up with two binomials, and if we multiply those together, we need to come up with the result. So let me go ahead and factor out a p and a p. We know that we did first time first, that'll be p squared, and that makes sense. Now let's think about this for a minute. We also know that our last term is going to be last times last gives us a result of last, right? So we look at this last term, and it is a 49. 49, I can take the square root of 49. In fact, the square root of 49 is 7. 7 times 7 is 49. If I go right in here and go ahead and put my 7s in there. Now I'm left with my insides, and my insides all come from the signs, pluses and minuses in here. So as I look back to this, my starting point here, I've got p squared minus 49, and notice that there is no single p term. What does that tell me? Well, that tells me that my p terms in my outside and inside are going to cancel each other out. So how do I figure out what that's going to be? Well, Notice here that the sign is negative. So that means whenever I do my multiplication, I have to have different signs. I have to have a positive and a negative, because a positive and a negative will give me a negative. If I've got two negatives, my result would be a positive, and if I have two positives, my result would be a positive. So they must be opposite signs. If I know that and I give them opposite signage, plus and minus, I see now that they will cancel each other out. See, first would be p squared, which is what I have. My outsides would be negative 7p plus 7p, which would give me a net 0p, which is what is here. There's no p, 0p. And then 7 times 7 is 49. With opposite signs means it's a negative 49. And so when I factor p squared minus 49, it factors down to p plus 7 and p minus 7 as my two binomials. Now, let's go ahead with number 9. Number 9 asks us to factor x squared minus x minus 72. I'm going to go ahead and set up my two binomials. I'm giving them each an x because I know that that's going to, first times first is going to be x squared. Now I'm looking for factors of 72. Remember we did this in class. I said I could have 1 times 72. I could have 2 times 36. I could have 3. What's 3 going to be? 24? Yep, 3 times 24. Could I have 4? Yeah, I could have 20. I could have 4, couldn't I? Because 80 would be 10, and it's 8 short of that, so it's 10 minus 2, 8. Let's see. 14, 16, 7, 20, 80 would be 20 minus 2, which is 18. Okay, that makes sense. 4 times 18 is 72. 5, no. 6, yeah, 6 goes into it. 6 times, well, 10 would be 60, so 12 would be 72. 7, no. 8, yes. 8 and, well, 10 would be 80 minus 1 would be 9. So 9 times 8 is 72. So now I have my factors of 72. 1 and 72, 2 and 36, and so on. So I know that this is going to be set up with one of those combinations. Now, because I have a negative sign here, I know that my signs are going to be opposites. Because if I were both positive, this would be a positive 72. If they were both negatives, this would still be a positive 72. In order to get a negative 72, I have to have a positive times a negative. So we've got that part set up. Now here's the trick. I need to have two terms that the difference between them is 1. Where do I have a difference of 1? Well, it's 8 and 9. 8 and 9, the difference between 8 and 9 is a difference of 1. And that is my coefficient of my middle term, 1. So I know that I'm going to be using this pair, 8 and 9. Now the next question is, which one goes in front of which sign? Well, in this case, I look to what is my resulting sign going to be? It's going to be a negative 1x. In order for me to end with a negative 1x, the difference between my first multiplication and my last multiplication needs to have a greater sign on the negative. So I'm going to go ahead and put a 9 in here and an 8 over here. Why? Because when I do my outsides, x times negative 9 is negative 9x plus insides 8x. So negative 9x plus 8x is negative 1x. And that's what I have here. So factoring out x squared minus x minus 72, the result is x plus 8, x minus 9. You may have written it the other way around, x minus 9, x plus 8. It's both equally correct. That is the answer to number 9. All right, let's get a clean sheet of paper and move on to number 10. Okay, number 10. 10 asks us to solve the equation 3 quantity x plus 4 minus 5 equals 6 minus x. Let's go through first and distribute out 3 across that binomial. And we're going to get 3x plus 12 minus 5 equals 6 minus x. First step. Now let's go through and combine like terms on both sides of the equal sign. I have my x terms over here, and there are no other x terms on the left-hand side of the equal sign, but there are 2 unit terms, plus 12 and minus 5. And so let me go through and do the math there, and the result is plus 7. 12 minus 5 is 7. And that equals 6 minus x. So now we've combined all of like terms on the left and the right-hand side of the equal sign. The next step is to get your variable you're solving for alone on one side of the equal sign. In this case, I tend to prefer the left-hand side, so I'm going to get all of my x terms to the left and all of my non-x terms to the right of the equal sign. Okay, so I want to get rid of the x term on this side and bring it across, and I do that by using the opposite operation. In this case, it's 6 minus x. I'm going to add x to both sides, and the result here then is 4x plus 7 equals 6. Next step, again, get the units term away from the term I'm solving for. So I'm going to subtract 7 from both sides, and the result is 4x is equal to minus 1. Now I have the variable I'm solving for, x, with a coefficient all alone on one side, and everything else on the right-hand side, in this case, a negative 1. To get rid of a coefficient, we're going to go ahead and divide by that coefficient, and we have to do the same thing to both sides. And so x is equal to negative 1/4. You may have seen it in the answer key, or you may have solved it and have written out the decimal. It's the same as negative 0.25. Same. All right, so x is equal to negative 1/4 for number 10. Number 11 asks us to simplify. So what we're going to do is just go through and combine like terms. We're not going to be able to solve it. We're going to end up with a much simpler form of the same equation. Number 11, simplify 4x minus 6 times the quantity 2 minus 7x. See, there's no equal sign. We're not solving it. We're just writing the same thing in a simpler way. Seeing in here I have a 6 times a binomial. Let me go ahead and distribute the 6 across the binomial. We have 4x minus 6 times 2 is 12. Plus, why plus? Remember, you're subtracting the entire resultant of this. Matter of fact, let me go ahead and write it another way, kind of a shortcut way. I'm going to add units or symbols of inclusion to help us with this. Let me go ahead and rewrite this as 4x minus 6 quantity 2 minus 7x. Okay? And we're going to keep the units of inclusion. We're going to solve inside, and then we're going to apply that negative sign out in front. So it's going to be 4x minus 6 times 2 is 12 minus, from the minus sign here, 6 times 7 is 42x. But now I need to go through and I'm subtracting 12 minus 42x. So it's 4x minus a positive 12 and minus a negative, which is same as a positive 42x. Now I'll go through and continue to combine like terms, and the like terms I have here are x and 42x. when I bring those together, it's going to be 46x minus 12. And I have no other like terms left. I've simplified it down. So 4x minus 6 times the quantity 2 minus 7x simplifies to 46x minus 12. These both have the same value. They're just different ways of writing the same thing. This one being much simpler. Number 12. Let me actually go over here. Number 12 says to evaluate. To evaluate means we're going to have we're going to have a mathematical string, and we're going to have a value that we plug in and then solve for that. So evaluate 5x minus 300 if x is, or x equals 2,000. So what I'm going to do is go through this mathematical string here, and I'm going to, every time I see the variable that I have a value for, I'm going to plug it in. So 5x minus 300 when x is equal to 2,000, I can rewrite that as 5 times x, which is 2,000, minus 300. Well, 5 times 2,000 is 10,000 minus 300, or 9,700. So 5x minus 300 when x is equal to 2,000 is equal to 9,700. For this section, next 4 problems, it says, tell whether or not the expression is a trinomial square. And if it is, factor it. If not, tell why not. Let's do a little bit of a review real quickly before we give the answers here, or work through them here. To determine if something is if an expression is a trinomial square, it needs to meet a couple conditions. First of all, its first and last term must be perfect squares. In other words, if you take the square root of the first and the last term, they have to be integers. If it's a number, or has to be a perfect variable, not a square root of a variable. So let's give a few examples, or at least work through if you remember. Let's say we have something that is first squared say we had something, I think for example we used in the lesson was we had x squared minus 10x plus 25, and what we said was if we look at the first term, in this case it's x squared, is x squared a perfect square? And we said in this case yes it would. Why? Because the square root of x squared is equal to x. Now we're going to look at the last term. The last term in this case is 25. Is 25 a perfect square? Well, yes it is, because the square root of 25 is 5. It's an integer. And so both the first term and the last term are perfect squares, and so this still has the possibility of being a trinomial square. But we also said the third condition is that the middle term, right in here, the middle term must be equal to 2 times the square root, or 2 times first two times the square root of the last. So the first has to be a perfect square, meaning we take the square root of it, we get an integer, or a rational number here. Here we got square root of 25, it works out to be 5. In this case, our third term, our middle term, needs to be 2 times the square root of the last term. Here, the last term was 25, the square root is 5. 2 times 5 is equal to 10. is our middle term 10? In this case, 10 times x. Is it? It is. It's 10, 10. So, we can factor that, or this is a trinomial square, and so we can factor that down. So let's do that. We're going to have the first term. In this case, it's going to be x. The last term is going to be our 5. Now we need to figure out how can we square this. What does the sign need to be in order for when we square this term, the result would be a negative term here and a positive term at the end. Now in order for us to get a positive at the end, remember our last terms would have to be either both positive or both negatives. They've got to be the same sign. For this term here to be a negative 10x, we would need to have the greater of, if we had two different binomials, the greater one would have to be the negative term, but in this case we're going to have a perfect square. It's going to be the same. Because it's a square, it has to have the same sign. And so the way this works itself out is this could be either a positive or a negative. If it was a positive, we would have a positive 10x. So it must be a negative. Because when we expand that back out, when we do it, and let's just do it longhand as if we're doing a FOIL, x minus 5, it would be x squared minus 5x minus 5x plus 25. The two insides would come up to minus 10x, which is what we have. So they must be a negative term. We don't have the option of having one positive and one negative because we're not doing two different binomials. We're doing a binomial squared. So the sign here is a negative. The operation is subtraction. And so the binomial then is x minus 5 quantity squared. Let's go on to do the numbers from, or the problems from test number 17, starting with number 13. 13, again, it's asking us to tell whether or not the expression is a trinomial square, and if it is, factor it. If it's not, tell why not. We have x squared minus 6x plus 36. Okay. First check. First term. X squared. Is it a perfect square? Yes. How do I know? Because x squared, the square root of x squared is x. The last term. Square root of 36. That is 6. It's an integer. So yes, the first term and the last term are both perfect squares. Now we get to assessing the middle term. The middle term would be 2 times the square root of the last, which is 36, right? So 2 square root 36, and that would have to be equal to 6. Our middle term, 6. So 2 times the square root of the last has to equal the middle term, or 6. Well, square root of 36 is itself 6, so 2 times 6 equal to 6. That is not true, and therefore 13 is not a trinomial square. Number 14. X squared minus 20x plus 100. The square root of the first is x. That checks. Square root of the last of 100 is equal to 10. So it's still possible. The third check is that 2 times the square root of the last equal to 20. Or 2 times the square root of 100 is the same as 2 times 10. Is that equal to 20? Well, 20 is equal to 20. Therefore, it checks. So yes, it is a trinomial square. What is that factored out? Well, our first term is going to be x. Our last term is going to be 10. And the sign here, because this is a negative sign, has to be a negative. So x minus 10 squared is the factorization of x squared minus 20x plus 100. Number 15. X squared plus 66x plus 1089. Well, the square root of the first term does check. The square root of the last term, and I don't have a calculator here, but a little bird tells me that the square root of 1089 is actually 33. So those two conditions check. What about the third condition? 2 times the square root of 1089, does that equal 66? Well, 2 times 33, does that equal 66? Yes, it does. So this is a trinomial square. What does it factor to? First term, x. Last term, 33. Quantity squared. What's the sign? Look to this place. It's a positive. X plus 33 squared. And number 16. X squared plus 142x minus 5041. Again, I don't have a calculator, so I'm glad I've got my little bird here to tell me. Square root of x squared is equal to x. And looking at my last term, I can see a problem already. Because we're considering whether or not it is a trinomial square, I notice here on this last term that the sign here, if you notice, is a negative. Now, what does a negative in the units term mean? When we think, if we were doing FOIL again and we were multiplying our last terms, if our last terms were both positive or both negative, our final term would be positive. In this case, whatever our binomials happen to be, in this case we're trying to be a perfect square, but let's say we just had two binomials. They don't have to be exactly the same, so it's not a perfect squaring. But if we had a negative 5041, what would that tell us? Well, that would tell us that our second term in both of them would be of different signage. One would be a positive and one would be a negative. That's the only way you can get a negative in that last term. And because we're talking about a perfect square, a trinomial square, this cannot be factored. Why? Because there's no way you can have something that's x plus something. In this case, let's say the square root of 5041. Let's pretend I knew that. Square root of 5041. If that was squared, when I do my FOIL, it's going to be this times itself, which is going to be 5041, but it's going to be positive because it's going to be a positive times a positive. Or let's pretend the sign was negative. When I get to the L in FOIL and I multiply my last terms, I'm still going to be multiplying a 5041 times a 5041, the square root of each, which gives me 5041. But I've got two negative signs, and that's still going to give me a positive. So because this second sign right there, the operation of subtraction, I can only get that if I have different signs, and I can't have different signs if I'm trying to do it as a trinomial factorization of a trinomial square. So 16, no, can't be done. 15 could be done. 14 could be done. 13 could not be done. All right, moving on. Number 17 is asking the question, and they want us to, let me get this squared away. There we go. It says, write the definition of square root. The definition of square root is that the square root of n is equal to the non-negative number for which the square root of n squared is equal to n. Said in class, you're not into imaginary numbers yet, so you're not going to be taking a square root of a negative number yet. So, the square root of anything is going to be the non-negative number of which the square of the square root is equal to the number itself. May look a little confusing, but it actually makes sense when you've been working through it. Number 18. 18 just says state the closure axiom for multiplication. And that reads, if x and y are real numbers, then xy is a unique real number. Remember, for it to be closed, the closure axiom of multiplication means for real numbers, not imaginary numbers, real numbers, meaning anything that does not involve a square root of a negative number. Okay? But anyway, real numbers. If I have a real number x and I have a real number y, when I multiply them together, x times y, if they're both real, the product of x times y is going to be a third number that is unique. It's not x or y. It's unique, and it also is a real number. So real times real equals a real. And that's why we say it's closed. Why? Because both of the two factors that are multiplied together that produce the third number, all three of those numbers are in the set known as real numbers. And when we do multiplication, it is closed because real times real produces real. Everything is in that set. Number 19, we've kind of danced around this the last couple questions. So this was number 17. Number 18, I just told you. Let's jump down to number 19. 19 says, explain why the negative square root of 25 is real and the square root of negative 25 is not real. Explain that. Well, first of all, we have to talk about what is the square root of 25. The square root of 25 is that number which, when it's squared, is equal to 25. What produces 25 when multiplied by itself? Well, it's number 5. So negative square root 25 could be rewritten as negative 5. Negative, think of it as negative 1 times the square root of 25, which gives us negative 5. However, here it's asking what number, when you square it, will give you negative 25. You might think it would be 5, but 5 times 5, positive 5 times positive 5 is positive 25. If you were to say negative 5, that would be wrong because negative 5 times negative 5 is also equal to a positive 25. And so there is no number that we know of that's real that we can multiply by itself and get a negative result. And that's where we come up with imaginary numbers, the not real numbers. Beyond the scope of this course, but I could rewrite this as the square root of 25 of negative 25 is the same thing as the square root of 25 times the square root of negative 1. The square root of negative times the square root of negative 1. Now that would simplify down to this. Square root of 25 is 5, but I still have to deal with the square root of negative 1. Well, we have a symbol that we use to abbreviate for the square root of negative 1, and it's the lowercase I. So in this case, we would rewrite 5 times the square root of negative 1 as 5i, or 5 imaginary. It's imaginary, it's not real. And that's where we talk about the real set and the imaginary set. So negative times the square root of 25 is equal to negative 5. But the square root of negative 25 is not a real number. And it can't be done within the scope of this course, this level of algebra. Number 20. Number 20 says, show that 3 and 5/8 is a rational number. Well, remember that a rational number is a number that can be described as a ratio between two integers. Ratio between two integers. So 3 and 5/8 could also be written as, well, 3 times 8 is 24 plus 5 is 29. So that's equal to 29/8. And 29/8 is a ratio between the number 29 and 8. It's, well, 29/8 is equal to 3 and 5/8. But because we can write it as a ratio between two numbers, it is indeed a rational number. Number 21. Show that the square root of 81 is a rational number. Well, square root of 81, that's equal to 9. 9 can be written as a fraction. That's just simply 9 over 1. It's the ratio between two numbers. And since it's the ratio between 9 and 1, square root of 81 is a rational number. Number 22 says, write an example of a positive real number that is irrational. What I'd like to do there is go ahead and give a square root of something which is not a perfect square. If I said the square root of 9, the answer would be 3. That's rational. I need something that's not rational. I need something that's not simply a relationship or ratio between two integers. The example they use in the answer key is the square root of 3. Now we can compute the square root of 3. If you have a calculator, you punch it in there, a slide rule, if you know what such a thing is, you can compute what the square root of 3 is, but it's not going to be an integer. It's going to be something between 1 and 2. 1 times 1 is 1, 2 times 2 is 4, so it's somewhere between 1 and 4, but it's going to be 1 decimal and then a whole bunch of decimal places. It's not going to be a simple ratio between two integers, and because of that, square root of 3 is an irrational number. Numbers 23 through 26, it looks like, ask the same basic question. Is the set closed under the given operation? And give an example showing clearly why your answer is correct. Number 23. Negative numbers under addition. Is it closed? Well, what it's asking here is if I have a negative number and I add to it another negative number, because the negative numbers are the ones I have to work with. That's my set, negative numbers. If I have a negative number and I add a negative number, will the sum be a negative number? Well, for number 23, the answer is yes. Is it closed? Yes. Or you could have written closed. closed. And give an example. Well, the book example here is, let's say we've got -3, and we add to that -4. We have a negative number added to that a negative number. And the result would be -7. See, if our set is negative numbers and our operation is addition, a negative number plus a negative number results in a negative number. Since our two first terms here with that operation result in a third term that is also part of the set again is all negative numbers, it's true, so yes, it's closed. The negative numbers are closed under addition. Number 24. The positive integers under division. In other words, if I have a positive integer and I divide it by another positive integer, will the result be a positive integer? And no, it's not closed. No, not closed. Get an example. Well, book example is a good one. If I have a positive integer, the number 3, and I'm dividing that by another positive integer, let's say we're dividing it by 4, we would expect the result to be another positive integer if it were closed. Positive integer divided by a positive integer results in a positive non-integer. And because the result is not within the set of the initial factors, it is not closed. So no, positive integers are not closed under division. Number 25. 25 asks, are positive numbers closed under division? Are positive numbers closed under division? The answer? Yes. It is closed. An example? Well, again, let's use 3/4. A positive number 3 divided by a positive number 4 is equal to a positive number 0.75. And now it didn't say positive integers. It just said positive numbers. If it had said positive integers, it would not be closed because 0.75 is not an integer, but it didn't say that. It said positive numbers. So a positive 3 divided by a positive 4 produces a positive 0.75. Is the result within the set from which the two factors come from? Yes, it is. And so yes, positive numbers are closed under division. Number 26. And for 26, the set is -1, 0, and 1. Those are the only three numbers you have to work with. And the question is that set closed under multiplication? So if we take any two of those numbers and multiply them together, will the result be one of the three numbers? The answer is yes. It is closed. And let's do a few. Since there's only three numbers, let's try several of them. If we have -1 times 0, the result is 0. Are these both in the set? Yes, they are. Is this in the set? Yes, it is. So anything times 0 is 0. So anything that has a 0 in it, in terms of the product, is going to be 0, and so the answer is going to be in the set. So the only thing we have left to work with are the +1 and -1. If I have -1 times -1, if I have +1 times +1, if I have +1 times -1, -1 times -1 is equal to +1, +1 times +1 is equal to +1, +1 times -1 is equal to -1. Are all of these answers in the set? Yes, they are. The set is closed under multiplication. All right, number 27, factoring problem. Let's go ahead and get a clean sheet. and get oriented. It's all backwards for me. That'll be good. All right. Number 27. Molly Factor starts working an algebra problem at a rate of 2 problems per minute. So the rate for Mally equals 2 per minute. 5 minutes later, her brother Benny starts working problems at a rate of 3 per minute. So rate Benny is equal to 3 per minute. Okay. If X is the number of minutes Mally has been working, so minutes Mally is equal to X. Write an expression in terms of X for the number of problems Benny has worked. Now we're going to need to relate the number of minutes that Benny has been working to the minutes that Mally has been working. And it says in the problem that Mally's starts working, and then 5 minutes later her brother Benny starts working. So Benny's time is whatever Mally's time is minus 5 minutes. So if X is the number for Mally, the minutes for Benny is equal to X minus 5. So at the 5 minute mark, Benny starts, his time would be 0, Mally's would be 5. When Mally's is at 10, Benny's at 5. When Mally's at 15, Benny's at 10, and so on. Okay. So if X is the number of minutes Mally has been working, write an expression in terms of X for the number of problems Benny has worked. Well, it's going to be the rate times time. The number of problems equals rate times time. In this case, the number of problems for Benny is equal to the rate of Benny times the time that Benny has. Well, the number of problems Benny is equal to the rate of Benny, and the rate of Benny is 3 per minute. And the minutes Benny has been working is equal to X minus 5 minutes. So 3 problems, a little bit of room there, 3 problems per minute times X minus 5 minutes. We can write that algebraically just simply by dropping the units and say these units here of minutes and problems. You'll learn later how these cancel each other out and leave us with problems. It's going to be equal to 3x minus 5 problems. So what that's saying is at any given time x, and x is the number of minutes that Mally has been working, at any given time x, you can compute how many problems Benny has completed with the formula 3 quantity x minus 5. Now there's a stipulation on this that the problem doesn't go into, but I just noticed it. It's assuming that Benny has actually been working. So if the number is less than 5, in other words, if at time is equal to 4, if you plugged a 4 in there, it'd be 3 times -1, and it would say Benny has done -1 problems. So this has really got a stipulation on it where x is greater than or equal to 5. But at any time past whenever Benny actually starts working, the number of problems that Benny has solved is 3 quantity x minus 5, where x is the number of minutes that Mally has been working. All right. Are we done? Yep, that is the end of test 17, numbers 1 through 27. I hope that's helpful. Hope you have a chance to go through it, review it, check your work, come to class with any specific questions you may have, and I will take test number 18 from you in class. All right, God bless.